Okay, so this is section 5.1 continued. This is the part 2 of it, series of solutions to ODEs. So last set of videos you learned about series, just general properties, sort of laying the groundwork for this. Now we're actually going to look at solving differential equations. What we're going to do is we're going to think about solving this type of differential equation. To do that, we're going to have to think about something called ordinary points. We're just going to define that. You're going to know that this method makes sense whenever those conditions are met, and that's all you need to think about for that topic. I'm going to write out the steps to solve this type of problem using an ordinary point, x0 equal to 0, and then we'll do examples. This is going to be like a sprint all the way through, and the videos might run long. I'm going to try to get in 2 full examples, but these problems are really long. So just bear with me, take breaks as you need them. So, problem to solve. So the problem we're going to be solving is the ODE. That's second order, y double prime plus p of x times y prime plus q of x times y equal to 0. This is one of those things where there's only a 1 in front of y double prime in order for us to have this p and this q. So if you have a differential equation and something's in front of y double prime, do that thing where you divide through by it before you proceed. And then what we need to talk about is what an ordinary point is. So the point x0 is an ordinary point. If p of x0 and q of x0 are analytic. So for you, that's just going to mean like, make sure it doesn't divide by 0, and all those other things that break functions. Just check those conditions. If x0 is one of these ordinary points, cool, can't write ordinary, one of these ordinary points, then sort of taking a solution y equal to the sum as n equals 0 to infinity, c sub n x minus x0 to the nth power is a solution to the ODE with some radius of convergence. X minus x0 less than r. And of course, if you wanted to get an idea of that radius of convergence, you could use that test that we learned last section. And really, when we say y is equal to all that stuff, if I've given you x0 is some special thing called an ordinary point, x minus x0 to the power n makes sense. Taking an infinite sum makes sense. The only thing that's not defined is Cn. So those coefficients, Cn, are what we don't know here. So solving the ODE becomes solve for Cn, so the differential equation is satisfied. And real quick, I want to make a connection to something that was really intuitive for you all during exam 2. So remember, we would say y equal e to the mx was a solution, and that became solve for m. What we're doing now is exactly the same thing. we're saying y equal to infinite sum n equals 0 to infinity Cn x minus x0 to the power n, a solution. It becomes solve for C sub n. Both of these just being basic algebra problems when you get down to it. It's just that this problem or this process is going to be a little bit more complicated because series are a little bit more complicated. And so I wrote out all the steps to solve this type of problem. And I think I can get through them in 5 minutes. So I'm going to squish them into this video. So steps to follow. And these are all going to be for x0 equal to 0. So the ordinary point we're going to talk about is x0 equals 0. You could repeat the same process for any point that is an ordinary point. 0 usually is 1. So that's why we're just going to practice this problem with this type of point. So step 1. Check that your ODE is y double prime with nothing in front of it, plus p of x y prime plus q of x y equal to 0. The reason that matters is because you check that the p and q evaluated at the ordinary point. So for us, that's p of 0 and q of 0 are analytic. We're just going to say are not a problem. If values of p of x, q of x would break at some x, that points to the size of your radius of convergence. So like if 0 is fine, but 17 is bad, then you know your radius of convergence is going to stop at 17. You don't technically have to check that part though, because you could instead do the ratio test to figure out the radius of convergence. So then you're going to assume y equal to the sum from n equals 0 to infinity, c sub n x to the n is the solution. That's that x minus x0 to the n for x0 equal to 0. Take derivatives of that solution. So you'll have y prime from n equals 1 to infinity, cn times n, x to the n minus 1, and y double prime is the sum from n equals 2 to infinity, cn times n minus 1, x to the n minus 2. So then from there, you're going to plug y prime, and y double prime into your ODE. And then you're going to manipulate the series, that's that process we talked about last class, into a single series with the same power x to the n and lower bound n equals k. So for example, that's going to look like n equals 1 or n equals 2. And then you're just going to solve for relationships using Cn that make the series equal to 0. So making that single series equal to 0, because sort of when you plug everything in here and combine it into one term, is going to be equal to 0. So basically that means everything attached to xn is 0. And then we'll just make this an extra long page, I guess. What you're going to have to do is you can have two unknown C0, C1 that you solve in an IVP. And then the rest of them are going to be given by that relationship. So those are the steps to follow. We're going to do some examples from here.